Today we will be discussing about skin effect. Like I pointed out in my earlier lecture on the behavior of the electromagnetic wave in a conducting medium, there is a decay of the electromagnetic wave as it traverses down the conducting medium. For a direct current, the electric current is uniform throughout the conductor, it has been observed. But for an alternating current, the current is not uniform. The electric field pushes away, like you can see it here. And it's the tendency of an alternating current to become distributed in a conductor in such a manner that the current density is maximum near the surface and this decreases exponentially as we move inwards. And the cause of this behavior is the eddy currents, which oppose the currents induced by the changing magnetic field, resulting in an alternating current. And this effect is observed in all the cases where the electromagnetic wave enters a conducting medium, obeying Ohm's law. And the depth to which the electromagnetic wave can travel is defined as the skin depth. We will be seeing it further. Like you can see, when the frequency of the electromagnetic radiation is small, the electromagnetic waves can penetrate deeper and you can experience current up to a greater depth. But as the frequency increases, the EM waves can't go that much deeper and are limited. More the increase in frequency, more skin effect is observed, and the more they are limited for entering the medium. So skin effect is basically the confinement of the electric current near the surface of the conductor, which results from the decay of the electromagnetic wave as it traverses down the conducting medium. You can see that the electric field is being pushed towards the surface. This is the behavior with the electromagnetic with the frequency. If the frequency is small, we have a greater skin depth. But the frequency increases, lesser skin depth. That means more. The depth is smaller up to which the electromagnetic wave will enter. As we can also see from this table, for a small frequency, we have a greater skin depth. As the frequency increases, the slow node decreases. We will see how it happens. Let's go to the theory part now. We know that the Maxwell's equation in a conducting medium are these four equations. And these equations are valid under the limit. The current density is a product of the conductivity and the electric field. So from the current equations 3 and 4, we get these two equations, which are in second order variables in space and time, both. And these equations are also called equations of telegraphy. Like we are seeing that the propagation of the electromagnetic waves in the conducting medium will depend on these equations only. How the fields are described by these equations vary, that will be the efficiency of the telegram that we are sending. So these equations will have a solution of the form given by these equations, the last terms. We have discussed this earlier in our previous lectures. And the wave vector here is a complex quantity. These are the real and the complex terms, and we can represent this also as a combination of the real and the complex and the real and imaginary term, which we can get after solving the wave equations, after substituting the electric field, getting the dispersion relation, and we can solve. For this, we have obtained this rather in our previous lecture. And this will result in an electromagnetic wave whose electric vector will be a combination of two terms. One is the routine wave propagation term, and other will be a decay term. We have obtained a similar solution in our previous lecture. So this represents the decay of the wave. And the distance where the amplitude of the wave, of the incident wave, reduces to 1 by Eth of the incident value is called the skin depth. And this 1 by E is nearly equivalent to 1/3 of the intensity. So if we have an intensity 1 at the interface medium where the electromagnetic wave is entering into the conducting medium, it will start on decaying, and the depth at which it becomes 1/3 or 1 by Eth of the the amplitude that was at the interface, that depth is called the skin depth. And the real part of the wave number gives the wavelength, propagation speed, and the refractive index, and the imaginary part is responsible for this decay. These are the resultant electric and magnetic vectors, where the direction of propagation is the Z direction, and the electric field is polarized along the X direction, and the magnetic along the Y direction. Like I said earlier, that the wave propagation is a vector is a complex quantity with the real and imaginary parts are there. And this is the phase, phi is the phase. The complex amplitudes of the electric and magnetic vectors are related to the Maxwell's equations. And the ratio of these amplitudes from the Maxwell's equation come out to be this. And finally, the electric and magnetic fields are represented by these equations, where we can see that the magnetic field and electric fields are not in phase. And the magnetic field lags behind the electric field by a phase phi. So in a conducting medium, the magnetic field lags behind the electric field. And we can see if the medium would not have been a conducting medium, the electromagnetic would have traveled the way it entered with a constant amplitude. But in the conducting medium, the amplitude of the electric vector and the magnetic vector both are decaying exponentially and gradually getting absorbed, the amplitude becoming zero. So we discussed the behavior of the electromagnetic wave and the importance of the skin effect, and calculated the skin depth. And here we end our lecture. Thanks for a nice hearing. Good day.